Stars are born in places the human eye could never reach without the help of telescopes. In dark, cold nebulae where time flows differently and space thickens with dust and gas. We look at them every night as if they were obvious, arranged across the sky like a choreography of light. And yet each one is its own world, its own story, its own flame burning in the vastness of the cosmos. From the closest star that gives us life to those silent points in the distance, whose light began its journey long before human civilization existed, stars are witnesses to everything that has been and everything that is yet to come. And that is why, when we look at the night sky, we are not truly seeing the past. We are seeing infinity. A star, though appearing in the sky as a tiny point of light, is inside a layered universe contained within a single pulsing sphere. Its structure is no accident, but a logical design built from forces that act with an intensity found nowhere else. At the very center lies the core, the most ruthless and most important place, because that is where its light is born. The temperature reaches millions of degrees, and the pressure is so unimaginable that hydrogen atoms are forced into fusion, merging into helium. It is there, in this space microscopic compared to the whole star, that the energy is created, energy that will later travel across the cosmic void to reach our eyes. The core is the engine of everything, a place that never knows rest. Just above the core stretches the radiative zone, a region where energy begins its hellishly long journey toward the surface. It doesn't travel simply. It bounces, is absorbed, and re-emitted over and over again. Each individual photon created in the core can spend millions of years in this layer before managing to move just a tiny step forward. You can imagine this part of the star as a labyrinth where light constantly loses its way. That is why the energy reaching us today may have been born when the first multicellular organisms were walking the Earth. Higher up begins the convective zone, the most dynamic part of a star's structure. The gas here never stays still. It behaves like a boiling ocean of plasma. Hot material rising toward the surface cools, then sinks back down only to be heated again. It creates colossal convection cells, some larger than the entire Earth. From the outside you can't see it, but the surface of a star is a vast, pulsating, roiling force. An endless dance of fire and gas, only at the boundary between the interior and cosmic space. Do we find the photosphere, what people call the star's surface, even though there is no solid boundary there at all? It is merely a thin layer through which light can finally escape into space. The photosphere reveals the star's temperament. Dark spots where magnetic fields twist and tangle, and grainy structures that mark the boiling convection below. Above the photosphere lies the chromosphere, a rarefied transparent layer endlessly trembling with waves of energy. And higher still, the corona, a cosmic paradox. It is so hot that its temperature reaches millions of degrees, many times hotter than the surface itself. We still do not fully understand it, though we know it is shaped by the violent, unpredictable physics of magnetic fields that behave like tightly wound springs. When they snap, they release explosions of energy more powerful than any weapon humans have ever created. A star is, then, a system of layers in which everything has its place and purpose. Each layer functions like a gear in a gigantic machine that shines only because gravity and pressure remain in perfect balance. When that balance breaks, the star expands, contracts, pulses, or dies dramatically, becoming a white dwarf, a neutron star, or a black hole. A star is not just a ball of light, it is a living, multi-layered organism in which matter dances to the rhythm of physics, making the night sky shine like a vast cosmic story. Asterisk. A star and a planet may look similar from afar, just points against the black backdrop of space, but they differ as fundamentally as fire and stone. A star lives, shines, burns within itself, while a planet merely reflects that light as it circles in its shadow. They are two entirely different stories, two separate destinies written into the matter of the universe. A star is born from the colossal collapse of a gas cloud, in which gravity compresses matter until nuclear fusion ignites in its core. From that moment on, it becomes a self-sustaining source of energy. Its interior is like an inexhaustible furnace in which hydrogen turns into helium, and light and heat emerge constantly, like a breath. A star shines because it must. Its existence depends on the balance between pressure pushing outward and gravity pulling inward. Every second it loses part of its mass, turning it into energy. It lives by its own rhythm, ages, changes color, grows or shrinks. As if it were a cosmic organism with its own biography, a planet is entirely different. It forms from the leftovers of that same cloud, but never reaches the mass required to ignite nuclear fusion. It is cold compared with a star, even if its interior remains heated by primordial energy or radioactive processes. It does not shine on its own. Its light is only the reflection of the star it orbits. A planet lives in shadow, dependent on what happens to its star, its temperature, radiation, distance. It may be rocky like Earth, gaseous like Jupiter, icy like Neptune, but its nature is always passive, shaped by the light that reaches it. A star is the actor, a planet the stage. The star creates energy, the planet transforms it. The star sets the rhythm of the entire system, days, seasons, climate, life, while the planet merely dances in its glow. When a star dies, its planets die with it or drift alone through eternal darkness. And as long as the star lives, planets remain only witnesses to its pulsing. Powerful life. In this difference lies the entire architecture of the cosmos. Stars are fire. Planets are ash. That sometimes, as in the case of Earth, can kindle its own spark life. A star shines because its interior is a place where matter is forced into behavior. We do not observe anywhere else in the universe. The energy it sends into space is not simply heat or burning as we know it from fire. It is the result of a process that begins deep in its core, where gravity compresses gas to the limits of nature's endurance. At this unimaginable density and temperature, hydrogen ceases to be the calm element known from chemistry and becomes the raw material for nuclear fusion. Hydrogen nuclei merge to form helium, but what matters most happens at the moment, when the mass of the products is slightly smaller than the mass of the ingredients. The disappearing portion of matter is converted into pure energy according to Einstein's equation. A star feeds on its own matter, transforming it into light. This is its source of life. Inside a star, energy is created in the form of high-energy photons and particles. But that is only the beginning of its journey. It does not escape from the core immediately. It is too dense, too chaotic there. It pushes through layers of plasma, colliding, scattering, losing energy, changing wavelength, as if hacking through a jungle made entirely of atoms. Sometimes it takes millions of years for this primordial energy to reach the surface. Only when it arrives at the photosphere can it escape into space, finally free. Finally the light we see in the sky. And this is why a star shines. It can constantly transform matter into energy. And gravity forces it to maintain the hell within. Most importantly, a star's light is not the result of burning in the chemical sense. A star does not burn anything the way wood or fuel does. Instead, it functions like a cosmic reactor in which fundamental forces bend matter beyond the limits of familiar behavior. Light is simply the byproduct of this extraordinary transformation. Proof of the balance between the force that wants to crush the star and the energy that pushes it outward. A star shines because, in its heart, the act of creating energy continues endlessly. And every ray that reaches us is a distant echo of that cosmic labor, an effort that never stops for as long as the star lives. The interior of a star is an arena of constant tension, where two powerful forces clash from the very first moment of its existence until its death. On one side is gravity, a relentless force, always pulling inward, always trying to compress the star into an unimaginably dense sphere. If it acted alone, the star would collapse instantly, shrinking like a deflated balloon until it became a dark, formless mass. But opposing it is internal pressure, born from the energy produced in the core. Every thermonuclear reaction not only creates light, but also exerts a subtle yet powerful push on the surrounding matter. This pressure tries to expand the star, keep its layers at a distance from the center, and prevent them from collapsing under their own weight. As a result, the star exists in a state of equilibrium, so precise that even the slightest change can alter its future. This equilibrium is not static. It is more like a dialogue that lasts for millions of years, a dynamic agreement between two opposing forces. If gravity begins to win, the star starts to contract, and this contraction increases the temperature and accelerates nuclear reactions. Then internal pressure rises, regaining its advantage. If, on the other hand, too much energy is produced in the core, The star begins to expand, and this expansion lowers the temperature, slows the fusion, and allows gravity to regain control. It is almost like a heartbeat stretched across cosmic time. Everything we see in the sky, the calm glow, changes in brightness, and even the star's future fate emerges from this delicate interplay. The balance between gravity and pressure determines whether a star remains stable like the sun, expands into a red giant, or collapses violently, leading to a supernova explosion. In truth, a star shines and endures only because these two forces maintain a constant, tense embrace. Gravity tries to close it, pressure tries to open it, and somewhere between those opposites its life, its light, and its extraordinary stability are born. Lasting for billions of years. The interior of a star resembles nothing from the everyday world. It is a place where physics stops being intuitive, where matter reaches such extreme states that it is difficult to compare it even to the hottest spark on Earth. Calling it gas would be as accurate as calling lava slightly warmed rock. A star is dominated by plasma, the fourth state of matter, impossible to touch, contain, or imagine without great effort. It is a mixture of free atomic nuclei and electrons, stripped of the bonds that normally form atoms. At temperatures of millions of degrees, everything is separated, torn apart, stripped of stability. Electrons don't orbit nuclei, they fly chaotically, like a swarm of sparks in a storm of fire. In such plasma, hydrogen and helium dominate, as they are the lightest and most abundant elements in the universe. But that is only part of the story. As a star ages, its composition begins to change. Every thermonuclear reaction in a star's core acts like a cosmic machine tool, shaping more complex structures from simple building blocks. First, hydrogen fuses into helium, the basic transformation experienced by all normal stars on the main sequence. But when helium becomes dominant and the hydrogen in the core runs out, the star begins to seek new fuel. The immense temperatures and pressures that arise when the star contracts under gravity open the path to more demanding reactions. Helium begins to fuse into carbon, carbon into oxygen, oxygen into neon, and then into heavier elements like magnesium or silicon. In the most massive stars, the chain of fusion continues, rippling through phases of instability, until iron begins to form in the core. And here something absolutely fundamental occurs. Iron is the limit. Its fusion does not produce energy. On the contrary, it consumes it. This means that for massive stars, iron becomes a critical point, the end of their capabilities. When the core begins to fill with iron, there is no longer any force capable of balancing gravity. Collapse begins, a dramatic, rapid process leading to a supernova. And in this phase, the magic of the universe's chemical diversity is born. A supernova explosion is so powerful that it enables the synthesis of elements heavier than iron, gold, uranium, platinum, iodine, tin, and even exotic elements like neodymium or europium. These elements, so rare, so vital for planets' biology and technology, are created in a fraction of a second. As the star's matter is brutally compressed and expelled into the void, everything heavier than iron in our bodies, the calcium in bones, the iron in blood, the copper in neurons, the gold in rings, the lead in batteries, the silver in electronics, is dust from ancient stars that ended their lives in cosmic explosions. Meanwhile, lighter stars like the Sun, though unable to produce such a rich palette of elements, also give back their treasures. When they die as planetary nebulae, they release carbon, oxygen, neon, and nitrogen, the building blocks of future planets, future atmospheres, and perhaps future life. Thus, the composition of a star is not just a mixture of atoms. It is the story of a cosmic forge in which matter matures, transforms, and gains complexity. Every element heavier than hydrogen and helium, absolutely everyone, is the product of previous generations of stars. Without them, the universe would be a dull, cold collection of simple gases, without planets, without chemistry, without biology, and without us. Stars are what give the cosmos color, mass, potential, and meaning, forging from plasma and fire the foundations of all existence. The birth of a star begins in a place that, at first glance, looks like nothing more than a chaotic, shadowy stain in space, a nebula. But that's only an illusion. These dark, dense clouds of gas and dust are, in reality, cosmic nurseries, places where the universe weaves its most important substance, light. Inside them lies a silence so deep that even photons struggle to break through it. Everything is cold, slow, sluggish. Hydrogen molecules drift beside grains of silicate dust, swirling aimlessly as if they've been waiting for a sign for billions of years. That sign is always gravity. No explosion is required, no cosmic spectacle. Sometimes a slight disturbance is enough, a shockwave from a supernova, the motion of a galaxy's spiral arms, or even a simple clumping of matter in one spot. Gravity begins pulling gas inward, and the nebula stops being a chaotic cloud. It starts to gather, to contract, to collapse. A protostar appears, a seed, barely a point within the massive cloud, yet already standing out with its growing brightness. Its interior becomes hotter and hotter as collapsing matter transforms gravitational energy into heat. It's as if the universe were pressing down with a vast spatial hand, squeezing, tightening, forcing the mass to reorganize. The more the protostar contracts, the faster its temperature rises, first to hundreds of thousands, then to millions of degrees. Around it, a disk of matter still swirls. From it, planets, moons, and asteroids may one day form, but that lies far in the future. For now, everything centers on the heart of the protostar. When its core reaches about 10 million degrees, a moment arrives that can be compared to striking a match in absolute darkness. Nuclear fusion begins, and hydrogen turns into helium. It is the ignition of a cosmic engine that will run for millions or billions of years. From that moment on, the star is truly born. A balance emerges between gravity, which tries to crush it, and radiation pressure, which tries to tear it apart. It is a delicate, precise dance of forces, and because of it, the star shines steadily, neither collapsing nor exploding, and that is why nebulae are so extraordinary. Hidden within their darkness is the greatest paradox of the cosmos. The darker they are, the more light they create. From seemingly thick dust emerge objects that will later illuminate galaxies. From cold, silent vapors arise scorching spheres of plasma that may one day warm planets and give rise to life. Before a star can shine in the sky, it must endure a long era of darkness, compression, and chaos. And when it finally ignites, it becomes everything the universe is in its most beautiful form, a place where darkness gives birth to light. Gravitational collapse is like the cosmic breath of the universe, slow, invisible, yet powerful enough to transform a shapeless cloud of gas into the core of a burning star. Contrary to appearances, this is neither an orderly nor a predictable process. Everything begins in chaos, and the first sparks of future light often arise from the universe's random gestures, so subtle that it's easy to overlook their true scale. Inside a nebula, a vast cloud of cold hydrogen and dust, there is perfect silence, uniform, undisturbed, as if matter were suspended in space-time without purpose. But this balance is an illusion, because even the slightest disturbance can break it. Sometimes it's a single fragment of the cloud becoming just a bit denser than the rest. Sometimes it's a delicate vibration caused by the motion of a spiral galactic arm. Other times it's shock waves, the most brutal messengers of the cosmos, carrying the echo of another star's death. When a supernova explodes, it sends out a powerful burst of energy that pushes, compresses, and stirs the matter in nearby clouds. Such a wave acts like a cosmic chisel striking soft clay. It creates densifications that attract more and more material. A single small difference is enough to trigger an avalanche. When a fragment of the cloud becomes even slightly denser, its gravity strengthens, pulling in more gas. With every attracted atom, the force grows, the process accelerates, and soon the minor densification becomes a collapsing sphere of matter. The cosmos is merciless here. Once something begins to fall inward, there is no turning back. Gravity knows no half measures. As the cloud shrinks, the matter inside starts moving faster and faster. Greater speed means rising temperature. Millions of years of cold and stagnation give way to rapid heating that resembles cosmic friction. The cold cloud of dust transforms into a glowing core, still hidden deep within the nebula's darkness. This interior, though not yet shining, is already like a pulsating embryo waiting for ignition. During this time, gravitational collapse is not uniform. Various fragments of the cloud curl into separate clumps, each capable of giving birth to a different star. A nebula does not create a single star, it often produces entire clusters. Disturbances, shock waves, turbulence, all of these shape future planetary systems, determining the mass of each forming star and its ultimate fate. The largest clumps, which gather the most material, will later become massive blue stars, burning fuel at a furious pace. Smaller, gentler ones, like the Sun, will live long and stable lives. Gravitational collapse is the foundation of star formation. Yet it is also an incredibly brutal process. When the core of a collapsing cloud becomes extremely dense, gravity compresses the matter so tightly that it no longer behaves like ordinary gas. Plasma forms, and the once thin, invisible cloud starts to resemble a tiny hell hidden in the darkness. And yet it is this seeming chaos, random shocks, waves from the depths of other stars, turbulence in galactic arms, that begins all order. Without it, there would be no light, no stars, no planets. Gravitational collapse is therefore not just a fall, it is creation. It is the moment when the universe takes a deep breath, compresses matter, and prepares it for the birth of something that will later shine in space as a bright point, a new star born from darkness and chaos. A protostar is a stage where a star is already someone, but not yet entitled to call itself a true star. It is something in between, like a cosmic teenager, growing rapidly, constantly changing, sometimes brightening, sometimes dimming, while powerful tensions form inside it, preparing it for adulthood as a stable star. At the moment gravitational collapse begins, the cloud of gas and dust becomes smaller and denser. A core forms, gradually gaining mass, because nothing in the universe attracts matter as efficiently as something that has already begun to collapse. Material swirls around it, creating an accretion disk resembling a giant whirlpool, except made of plasma and dust. This disk is like a cosmic cafeteria. The protostar feeds from it, and its food is gas, mostly hydrogen. The more it gathers, the more massive a star it may become. During this time, its temperature rises dramatically. Initially, the interior has only a few hundred degrees, then thousands, hundreds of thousands, and eventually millions. All because the matter falling inward is compressed and heated by gravitational energy. It's as if the universe were grinding a gigantic ball of gas in a mortar until it becomes glowing and dense. The protostar does not shine due to nuclear reactions yet, but it emits heat and light because of the immense temperatures produced during collapse. It is said to shine from gravity, not from fusion, and that's what distinguishes it from a true star dot. As it grows, it begins to clean its surroundings. Radiation and stellar winds push out leftover gas and dust from the nearby region, slowly revealing its shape. But the process of gathering mass continues. If the protostar is large enough, its gravity becomes so strong that it pulls in every loose hydrogen atom from the surrounding disk. This process is irregular. Sometimes the mass accretes smoothly. Other times the protostar releases violent bursts of energy. Young stars in this stage behave like martial artists, throwing jets of plasma into space, and their brightness can change within hours. It is a time of violence and constant maturation. Inside, the drama intensifies. Temperature, density, and pressure all rise. Every day of this cosmic adolescence brings the protostar closer to a critical point. Eventually, the core heats to over 10 million degrees. At that moment, childhood ends, and the protostar phase concludes. Hydrogen fusion begins, the first breath of an adult star. This process is like lighting a universal fuse. In an instant, the balance of forces changes. Radiation pressure finally stands equal to gravity. The star establishes a new, stable, luminous state. The protostar matures into a main sequence star, an object that will shine for millions or billions of years. But before that can happen, it must pass through this turbulent period of mass gathering, temperature pulsation, and struggle against its own gravitational weight. This is a chaotic, intense, and necessary stage, because without this youthful fury, no star could ever be born. Asterisk. The moment of nuclear ignition is the instant when the cosmos turns on its light. A protostar, which until now only glowed faintly under the pressure of its own gravity, eventually reaches an internal threshold after which everything changes. Inside it, the temperature rises relentlessly, first thousands, then millions of degrees, until the core becomes so unimaginably hot and so brutally dense that hydrogen atoms stop behaving like quiet, timid particles. They begin to collide with a fury no material in the universe could withstand. At some point, hydrogen yields to this pressure. Electrons are stripped away, protons and neutrons begin to shift and jump between one another, and the barriers of electromagnetic repulsion that normally keep atoms apart are overcome. And then, the reaction occurs, the one that has sustained the glow of galaxies for billions of years: nuclear fusion. 4 protons merge into a helium nucleus, and the excess energy is sent outward as radiation. It is this very energy that illuminates the star. Ignition is not a quiet process. It is more like breaking through internal resistance, as if the star reached its own limit and suddenly discovered it could create light from within itself. Until now, it shone faintly because it was heated through gravitational collapse. Now, however, it begins to generate energy in an entirely new way. Its core becomes a reactor whose power is so stable that it can last for billions of years continuously, balancing pressure against the pull of gravity. This moment of ignition marks the birth of a true star. From this point on, its brightness no longer depends on chaotic, violent processes, but comes from a precise, almost mathematical balance of forces. Radiation pressure pushes outward, gravity pulls inward, and the result is such a perfect equilibrium that the sun, which has been shining for 4.6 billion years, still persists in it like a perfectly calibrated beacon. Nuclear ignition is therefore more than just a physical phenomenon. It is a passage from darkness to light, from chaos to stability, from protostar to a fully fledged cosmic object. From this moment on, the star does not merely exist, it shines, and its light travels across space so that one day, millions of years later, it may reach someone's eye and tell the story of its birth. Life on the main sequence is a star's longest, most stable, and most peaceful era, a kind of cosmic adulthood in which everything operates like a perfectly oiled machine. Once nuclear fusion ignites, the star reaches an equilibrium between gravity, which constantly tries to compress it, and radiation pressure, which tries to push it outward. This balance is so precise, so delicately tuned, that it can last millions, billions, or even trillions of years. This is why most stars spend nearly their entire existence in this phase. It is the only stage in which their internal forces cancel out perfectly, allowing them to shine steadily and predictably. At the heart of the star, hydrogen is continuously fused into helium. This simple process is like breathing, repetitive, orderly, and essential for survival. As long as there is enough hydrogen in the core, the star remains stable. The cosmic reactor runs calmly, and the radiation flowing outward balances the inward pull of gravity. This is a state that requires no dramatic gestures from the star. It simply exists, shines, warms its surroundings, emits stellar winds, and its light permeates space like a rhythmic heartbeat. But how long this phase lasts, and what the star's later history will look like, depends on a single parameter that governs everything: mass. The mass of a star is its destiny. It determines how bright the star will be, how quickly it burns its fuel, how long it will survive, and most importantly, how dramatic its death will be. Low-mass stars, like red dwarfs, burn their fuel slowly and calmly, like someone who has all the time in the universe. They can shine for trillions of years, longer than the universe has existed so far. Their hearts beat quietly, nuclear reactions proceed at a moderate pace, and this makes them incredibly long-lived. Like cosmic hermits for whom time barely exists, stars of medium mass like the Sun burn their fuel faster. They live for billions of years, but do so steadily and without haste. Their evolution is well-ordered, and their main sequence lifetime is long enough for planets to form and remain stable around them. And on some of those planets, like Earth, life can emerge. Massive stars, on the other hand, are the sprinters of the cosmos. They live intensely, brightly, spectacularly, but briefly. Their cores consume hydrogen at an astonishing rate, because greater mass means stronger gravity, and stronger gravity requires higher radiation pressure to maintain equilibrium. And higher pressure means faster nuclear reactions. Such a star shines thousands of times brighter than the Sun. Yet its life lasts only a few million years, a mere blink on the cosmic timescale. The main sequence is therefore the central chapter of a star's cosmic biography, its longest, calmest, and best organized period, yet entirely governed by mass, which acts like an invisible fate inscribed within the star. But every star, regardless of its size, eventually exhausts its fuel. And when the hydrogen runs out, the balance breaks. And the next, far more dramatic. Chapter begins, one in which mass once again determines whether the star will fade gently or die in an explosion that shakes the cosmos. Small stars and stellar giants represent two completely different approaches nature uses to accomplish the same task, turning hydrogen into light. Although all stars use the same fuel and obey the same physics, the way they do it depends entirely on their mass. And mass determines everything: the core temperature, the rate of fuel consumption, brightness, lifespan, and ultimate fate. It is mass that allows some stars to last billions or even trillions of years, while others burn so intensely that they extinguish themselves after just a few million. Small stars are like thrifty caretakers. They consume fuel slowly, wisely, and in a steady rhythm. Their cores have lower temperatures and pressures because gravity does not squeeze them as intensely as it does larger stars. This means nuclear reactions are fewer and proceed at a slower pace. Red dwarfs, the most common type of star in the galaxy, can burn hydrogen so efficiently that their supply lasts trillions of years. On a cosmic scale, that is eternity, these stars will still shine long after the sun has vanished, and even when the universe becomes an entirely different place. What is more, small stars burn their fuel so evenly that their entire interiors take part in the reaction. Nothing is wasted. Energy escapes slowly and precisely. And these stars age so gradually that none of them has yet reached late evolutionary stages. The universe is simply too young. Giants, on the other hand, live as if in constant haste. Their large mass means gravity crushes them with enormous force. So to avoid collapsing, they must instantly generate tremendous radiation pressure. And that means one thing: the core must work at full power. Nuclear reactions occur at a frenzied pace, hundreds or thousands of times faster than in small stars. Under such conditions, hydrogen disappears rapidly, like fuel in a jet engine pushed to maximum thrust. This is why massive stars, though brighter and more impressive, live extremely short lives. A star 10 times more massive than the sun may shine 1,000,000 times brighter, but its life often lasts only a few million years, a tiny fraction of what awaits smaller stars. The paradox is simple: the larger the star, the faster it dies. The very mass that gives it power and brilliance is also its doom. The overwhelming rate of fuel consumption leads to rapid exhaustion, and the later stages of such stars' evolution are dramatic, full of violent transformations and ending in spectacular supernova explosions. Small stars, modest and calm, last incomparably longer, living their slow, steady lives without fireworks. On a cosmic scale, it is a simple yet unforgiving mechanism. Low-mass stars live long because they burn slowly. High-mass stars live short because they burn fast. Their fate is written in their mass from the moment they are born, and nothing can change it. The colors of stars form one of nature's most beautiful palettes, subtle, yet precisely governed by the laws of physics. To the eye, the night sky seems full of white points of light, but that is only an illusion caused by great distance. Seen up close, we would witness a true rainbow of temperatures, from the blazing blue edges of the hottest stars to the cool red glow of those barely smoldering. Each color is a signal of how hot a star's surface is, how massive it was at birth, how quickly it burns its fuel, and at what stage of life it currently exists. Color is not an ornament, it is information encoded in light. A cosmic fingerprint. The hottest stars are blue and azure, true furnaces of the cosmos. Their surface temperatures reach up to 25,000 to 50,000 Kelvin, and sometimes even more. They shine so intensely that their energy pours out like a wave of fire. In the sky, these gigantic, massive objects are rare. Because their lives are short, they consume hydrogen at a frantic pace, as if burning themselves up all at once without saving anything for the future. Their light is the strongest in the entire spectrum. They emit vast amounts of ultraviolet radiation, and their brilliance can dominate an entire stellar region. Blue stars are cosmic sprinters, fast, bright, and short-lived. Just behind them are white stars, less hot, though still enormously energetic. Their temperatures reach 10,000 to 15,000 Kelvin, giving them a cool, almost crystalline glow. Their light contains less ultraviolet radiation, yet remains highly energetic. These are often young main sequence stars or more evolved objects that have already undergone part of their evolution. White stars are more common than blue ones, but still far rarer than yellow or orange stars. It is one of the colors in which physics distributes light most evenly across the spectrum, which is why we perceive them as very bright and pure. Yellow stars, such as our Sun, reach temperatures of about 5,500 to 6,000 Kelvin. In this part of the spectrum, the star's energy is more balanced. They emit enough green and blue light that the human eye perceives them as slightly golden. This color does not result from the star being yellow, but from how the wavelengths of light emitted by its surface blend together. Yellow stars represent stability, calmness, and longevity. They are massive enough to shine brightly, yet not so massive that they burn themselves out too quickly. These are the cosmic hearths best known in culture: warm, steady, and reliable. Even cooler are orange stars. Their temperatures drop to around 4,000 Kelvin. Although they still emit white light, the shift of their spectrum toward red gives them a warm, honey-colored glow. These stars, slightly smaller than the Sun, are particularly interesting from an astrobiological perspective because they combine slow fuel consumption with long-term stability. Their lifespans reach tens of billions of years, offering their planets far more time for the evolution of life than our Sun ever could. At the end of the cosmic palette, we find red stars, the coolest and at the same time the most numerous. Some have temperatures of only 2,500 to 3,500 Kelvin. These are red dwarfs, tiny, quiet, faint on a galactic scale, yet absolutely dominant in number. Their color is the result of long wavelength light emitted by their cool surfaces, a soft muted glow of embers, not flame. Although they are weak and difficult to spot from afar, they are the backbone of the galaxy. They live so long that they will likely be the last shining objects, when all other stars have long since gone dark. Red stars can also be enormous giants in their final stages of life. Then they radiate more intensely, but their color remains reddish, caused by the swelling and cooling of their surfaces. A star's color is nothing more than an indicator of its temperature and age. Young, massive stars are blue. More mature ones with balanced masses shine white or yellow, and the smallest and oldest glow red. The cosmos needs no pigments. Radiation and temperature are enough. Thanks to them, the night sky is not only beautiful but also full of information encoded in the colors of light that travel through time and space to tell us the story of their source. Asterisk. The end of life for small and medium-sized stars is like the slow, dignified extinguishing of a cosmic fire. There are no bursts or dramatic explosions. Yet there is an extraordinary transformation that stretches across millions of years and reveals the hidden mechanisms of the universe's evolution. Such a star, similar to our Sun, passes through its aging cycle with a dignity and monumentality incomparable to anything on Earth. Its fate is determined by one simple rule: eventually, it will run out of fuel. And when the hydrogen fire in its core begins to fade, the star becomes something entirely different from what it was for the majority of its existence. For billions of years, the star steadily fused hydrogen into helium, maintaining a balance between the pressure flowing from its glowing interior and the force of gravity, constantly trying to crush it. However, at some point, the hydrogen reserves in the core become too small to sustain this previous stability. The core of the star gently collapses, the temperature rises, and the outer layers, instead of contracting, begin to expand uncontrollably. The star swells like an overfilled sail and enters the red giant phase. Its diameter can grow hundreds of times larger, engulfing nearby orbits and changing everything around it. From a small yellow sphere, it becomes a vast, cool, reddish glowing bubble whose surface trembles with convection and pulsations. During this period, processes occur that cannot be seen but may be described as a throbbing chaos. The star's core, now dominated by helium, heats up to such a high temperature that the next stage begins: the fusion of helium into carbon and oxygen. This is a short phase, usually much shorter than the hydrogen-burning era, yet so intense that it can alter the internal structure of the star. Despite this new energy source, the outer layers remain unstable. The star begins to lose mass in the form of powerful stellar winds that peel it away layer by layer. These winds are slow but relentless, as if the star were shedding its old, heavy coats while preparing for an entirely new form of existence. Eventually, the star can no longer hold onto its bloated, loosely bound outer layers. They drift off into space, forming a spectacular structure, a planetary nebula. The name is misleading and historical, for a planetary nebula has nothing to do with planets. It is a round, delicate, colorful shell of gas expanding at a speed of a dozen or so kilometers per second, glowing thanks to the radiation of the star's intense core. It is one of the most beautiful astronomical phenomena, a momentary monument to the death of a stellar giant. A scene full of colors produced by ionized gas dot at the center of this expanding structure remains what was once the heart of the star, a white dwarf. It is small, extremely dense, about the size of Earth but with a mass equal to half the Sun, and sometimes even more. No thermonuclear reactions occur in its interior anymore. It is a naked core, glowing, hot, slowly cooling. Its temperature initially reaches over 100,000 Kelvin, but over time its radiation fades. The white dwarf is the star's last breath, its final stage, in which only residual heat continues to glow. Such an object may exist for trillions of years, gradually cooling into a black dwarf, a hypothetical form that does not yet exist in the universe because too little time has passed. This ending is peaceful yet dramatic in scale. From a small star arises a luminous nebula. From a great red giant remains a tiny ultradense core. In this process, the cosmos recovers the materials the star created within its interior. Carbon, oxygen, and other elements formed during its life are released into interstellar space, eventually becoming the building blocks of new stars, planets, and even life. The death of such stars is therefore not an end, but the beginning of a cycle that ensures the universe continually renews itself. This is the fate awaiting our sun as well, not a violent explosion, but gradual expansion, the sky brightened with a red glow. And finally, the remnant of a tiny white heart burning for billions of years. Within the death of small and medium-sized stars lies a quiet poetry, the peaceful surrender of what they once forged inside themselves, so that new generations of cosmic objects may exist. When a massive star nears the end of its life, it doesn't just quietly fade away like a small candle. Instead, it's more like a colossal torch that, in its final blaze, burns so brightly its death is etched into the very fabric of the galaxy. A massive star's life is one of constant tension, immense mass, immense energy, immense pressure, and so its end must be equally spectacular. It doesn't fade quietly. It explodes with a force that can, for a moment, outshine all the other stars in its galaxy combined. But before that grand finale, the star goes through a long, dramatic aging process. It transforms into a supergiant, expanding to unbelievable sizes. If our sun were to become a red supergiant, its outer layers could swallow Mars, maybe even Jupiter. Despite its colossal size, the surface of the star becomes cooler, a deep, dark red, and it constantly pulsates, as if the entire structure is taking heavy breaths under the pressure of the energy trapped inside. Meanwhile, the star's core begins to look like an onion. Layer after layer, it burns progressively heavier elements. First hydrogen, then helium, then carbon, neon, oxygen, and silicon. Each stage is shorter, more violent, and demands ever higher temperatures. The star is hurtling toward its demise like a runaway train with no brakes. Everything builds up to the one moment that seals the star's fate, the formation of iron in its core. For a star, iron is a dead end. Fusing iron doesn't release energy. It consumes it. In that instant, the star loses the one thing that held it together its entire life, the outward pressure balancing gravity. This delicate balance shatters in a fraction of a second. The core collapses in on itself at thousands of kilometers per second, and the outer layers of the star follow like a cosmic avalanche. This is the moment the universe seems to hold its breath. Then, the collapsing core hits an unbreakable wall, either due to powerful quantum forces or the formation of dense neutron matter. It abruptly stops, and the cataclysmic shockwave rebounds from its surface, racing outward through the falling layers. This is the birth of a supernova. The brightness of a supernova can exceed that of hundreds of billions of stars. The energy it releases in just a few seconds is more than what our sun will radiate over its entire 10 billion year lifespan. Supernova explosions can be seen from distant galaxies, and throughout history, people have recorded ones so bright they were visible with the naked eye in broad daylight. But a supernova isn't just a spectacular display of cosmic force. It plays a vital role in creating the universe as we know it. Inside this furnace, at temperatures of billions of degrees, the heaviest elements are forged: gold, uranium, platinum, silver. All the precious materials that build planets, fill oceans, and even form our own bodies were born in the cosmic roar of a dying massive star. The explosion scatters these elements across vast distances, seeding the galaxy with the raw materials needed for new worlds and new life. When a massive star dies, its final act is also an act of creation. From the chaos of the supernova explosion, objects so extreme emerge that it is hard to believe they exist in the same universe as our peaceful planet or gentle red dwarfs. What's left behind is the star's signature, a fingerprint pressed into the very structure of spacetime. And although the three main remnants, a neutron star, a pulsar, and a black hole, all come from the same process, each one represents a different level of cosmic extremity. To really understand them, we have to go back to that split-second moment when the core of a massive star collapses. As the core implodes, the gravitational pressure becomes unimaginable. Electrons are squeezed so hard that they are forced into protons. The result is both simple and terrifying. Protons and electrons merge to become neutrons, and the entire core transforms into a uniform, super-dense block of matter. This is where the first possibility arises: a neutron star. It's an object unlike anything we can comprehend. A single teaspoon of its matter would weigh more than a giant iceberg. The entire star is only the size of a large city, maybe 20 or 30 kilometers across. Yet its mass is greater than that of our sun. The density is so extreme that space around it is visibly warped, and time itself flows more slowly. It isn't a star, in the traditional sense. It's like a single gigantic atom made entirely of neutrons, blown up to impossible dimensions. Its surface is a hard crystalline crust, while its interior is a bizarre, superfluid liquid that conducts energy and magnetic fields with an efficiency we can't replicate on Earth. But neutron stars aren't always quiet. Some inherit so much spin from their parent star's collapse that they rotate at incredible speeds. Imagine a city-sized sphere spinning hundreds of times every single second. That's a pulsar, a neutron star that has become a cosmic lighthouse. Its magnetic field is billions of times stronger than Earth's, powerful enough to channel streams of charged particles into narrow, laser-like beams. As this spinning lighthouse rotates, its beams sweep across space. If Earth happens to be in the path of one of these beams, our radio telescopes detect regular, pulsing signals. This is why pulsars are so astonishingly precise. Their signals can be more accurate than our most advanced atomic clocks. But even pulsars aren't perfect. Sometimes they glitch, suddenly speeding up or slowing down, as if we're witnessing a giant cosmic engine shifting gears. Each pulse is a reminder of the violent, beautiful death of a star that once lit up the galaxy. What happens when a massive star runs out of fuel? Its death gives birth to some of the universe's most extreme objects. One possibility is a neutron star. But even a neutron star has its limits. If the star's core is too massive, nothing can stop its collapse. No particles, no structure, no stopping point. This is how a black hole forms an object completely unlike anything we know. It's not a star or a sphere. It's a region where gravity warps spacetime so intensely that nothing, not even light, can escape. Its boundary is called the event horizon. It's not a physical surface but a point of no return. Cross it and you're gone forever. For an outside observer, time at the horizon seems to stop completely, but black holes aren't just cosmic monsters. They are a part of the universe's architecture. They grow, they collide, and they can create accretion disks so hot they outshine entire galaxies. They are both the darkest and the brightest objects we know. And each one, no matter how large, started as a star whose collapse couldn't be stopped. So a neutron star is all about density, a pulsar is about rotation and magnetism, and a black hole? It's matter collapsing until physics as we know it breaks down. 3 different answers to one question. What happens when a massive star dies? These endings are actually new beginnings. The death of a massive star creates the foundation for the universe's most powerful structures. Without it, we wouldn't have the gold in our rings, signals from pulsars, or black holes that test the limits of reality. The universe is full of wonders, but sometimes we need to look at its strangest creations to truly understand its cosmic imagination. Let's shift our gaze from the giants to the quiet army of the cosmos. Red dwarfs. They're inconspicuous, faint, and too dim to see with the naked eye from Earth. Yet, They are the most numerous and arguably the most important stars in the universe. If you imagine the galaxy as a vast city, red dwarfs are the ordinary houses, lining up in endless rows. They make up about 3/4 of all stars in the Milky Way. This means most places where life could potentially arise orbit these modest, long-lived embers. They are small, usually between 8 and 50% of the sun's mass, and relatively cool. If you stood on a planet orbiting a red dwarf, the sky would have a soft orange glow, like a permanent sunset. But what they lack in brightness, they make up for in endurance. No other stars live as long. A red dwarf burns its hydrogen fuel with remarkable efficiency. Unlike larger stars, a red dwarf constantly mixes its fuel, so almost all its hydrogen is available for fusion. The result? A lifespan that is almost absurd. The smallest red dwarfs can exist for trillions of years, far longer than the current age of the universe. This means that every single red dwarf that has ever formed is still shining today. Not one has had time to die. But these stars are full of contradictions. Though small and stable, they can be surprisingly violent. Many young red dwarfs are flare stars, unleashing powerful eruptions of energy that could scorch nearby planets. And because they're so dim, a planet's habitable zone is very close, often close enough for it to become tidally locked. This creates worlds with one side in perpetual daylight and the other in eternal night, with only a narrow twilight strip suitable for life. Even so, scientists look to red dwarfs with hope. There are so many of them that even if only a small percentage host stable planets, the numbers still favor the possibility of life. Plus, their small size makes it easier to spot planets passing in front of them. Red dwarfs are like small campfires scattered across the galaxy, quietly sustaining the cosmic darkness. Who knows, perhaps in the shadow of one of those modest suns, life is looking up at an orange sky, wondering if other worlds exist. Now, let's talk about white dwarfs. They are the fossilized hearts of ancient suns, the final glow of stellar life. These are what's left after stars like our sun have burned through their fuel, expanded into red giants and shed their outer layers. All that remains is the core, hot, dense, and with no nuclear fire left to burn. And yet they still shine, radiating away their leftover heat like fading embers in the void. Imagine a sphere only slightly larger than Earth, but so dense that a single teaspoon of its material would weigh as much as a mountain. This isn't a metaphor. It's physics. White dwarfs are made of matter so compressed that atoms are crushed together. What stops them from collapsing further isn't gravity, but a strange quantum force called electron degeneracy pressure. It's a law of physics that says electrons refuse to be squeezed any closer together. When they first form, white dwarfs can be incredibly hot, with surface temperatures of hundreds of thousands of degrees. But with no fuel left, all they can do is cool down. Over millions and billions of years, they slowly fade, releasing their heat into space. During this long process, they become cosmic archives. Their chemical composition tells us about the star that created them, and their temperature helps us determine their age, like cosmic clocks ticking in the silence. The most fascinating thing is their lifespan. Before a white dwarf finally cools into a hypothetical black dwarf, a cold, dark, invisible cinder, trillions of years must pass. That's far more time than the universe has existed. This means every white dwarf we can see is still in its youth. Not a single one has had time to completely fade away. They are a quiet, dense, and enduring reminder that the death of a star isn't always an end. Sometimes it's a frozen memory, drifting through eternity. Finally, let's explore the cosmic almost stars. Brown dwarfs. These are objects that started their journey like any other star, from a collapsing cloud of gas and dust, but never quite made it. They are the undercooked stars of the universe, stopping just short of igniting the full, stable fire of nuclear fusion. For a star to shine, its core needs to reach about 10 million degrees to fuse hydrogen into helium. Brown dwarfs have too much mass to be called planets, but not enough to kickstart this process. They are the in-betweeners larger than Jupiter, but too light for gravity to generate the immense pressure needed for stellar ignition. For a brief period after they form, they can fuse a light hydrogen isotope called deuterium. But then, the nuclear fire goes out, and a permanent silence falls. So what are they exactly? They're not stars, but they're not planets either. They glow faintly, mostly in infrared light, radiating away the heat from their formation. They're like celestial embers that never caught fire. Because they are so dim and cool, they are incredibly difficult to find. We've only been discovering them in recent decades, thanks to advanced infrared telescopes. Finding them is like searching for a single dark coal in a vast dark field at night. But each one we find adds another piece to the puzzle of star formation. They show us that the line between a giant planet and a tiny star is blurry. They are the universe's failed stars, but their story isn't one of failure. It's a story of how something unique and mysterious can form in the vast expanse between worlds and suns. Brown dwarfs remind us that in the cosmos, even the in-betweens have a fascinating story to tell. From black holes to red dwarfs, the universe is filled with an incredible diversity of stellar objects. Each one tells a part of the grand cosmic story. Have you ever looked up at the night sky and wondered about the stars that failed? Imagine a star that never quite made it, a cosmic ember left glowing in the dark. These are brown dwarfs, the so-called failed stars. They are born from the same cosmic nurseries as our sun, but they just don't have enough mass to ignite the nuclear fires that make a star shine. And yet brown dwarfs live. They still emit a faint residual heat, a slow cooling of matter that never had the chance to become a sun. At first, they might appear reddish or orange, but as they cool over billions of years, they drift into deep shades of violet and burgundy, eventually becoming almost invisible. We can only spot them in infrared light, where their delicate thermal glow gives them away. They're like glowing stones buried in the ashes of a campfire. They don't burn, but they still hold the memory of a former heat. Inside these strange objects, extraordinary physics unfolds. As a brown dwarf cools, exotic chemistry takes over. Imagine clouds made of iron vapor or droplets of molten rock, floating in an atmosphere that's somewhere between a planet and a star. They are cosmic laboratories where nature experiments with what it can create under extreme conditions. Brown dwarfs drift through our galaxy in enormous numbers, hidden in the shadows. They might be lurking on the edge of planetary systems or wandering alone between the stars, quiet, invisible, and slowly fading. They are the dark siblings of stars, born from the same material but never reaching stellar maturity. Their existence is crucial because they show us that the universe isn't just about success or failure. It's a spectrum of possibilities where every outcome has its place. Brown dwarfs are a beautiful testament to the universe's fondness for leaving some stories unfinished. Now, let's shift our gaze to the artists of the cosmos. Variable stars. These aren't calm, stable suns like ours. They pulse, they flash, they erupt in rhythms that give the universe a sense of drama and unpredictability. Observing them is like peering into the very heart of a star, because every change in brightness is a story written in light, a story of internal struggles, crises, and storms. The most harmonious among them are the pulsating stars. Their light doesn't just switch on and off. It rises and falls in gentle waves, as if they were breathing. Inside, layers of gas heat up, expand, cool down, and contract, setting the entire star pulsing. Each cycle is like a cosmic heartbeat, and some are so regular they've become cosmic clocks. Cepheid variables, for instance, pulse so consistently that astronomers use them as rulers to measure vast distances across the universe. Their rhythm isn't random. It's the result of a fundamental battle between gravity and pressure. Then there are the flare stars. They behave very differently, experiencing short, violent bursts of brightness. It's like someone flipping a light switch on and off without warning. Powerful magnetic fields on their surface suddenly release enormous amounts of energy in massive flares, making the star many times brighter for just a moment before it returns to normal. Their chaotic nature comes from turbulent plasma and unstable magnetic fields. But the most emotionally charged are the explosive stars, the true volcanoes of the cosmos. These objects store up energy like a coiled spring and then release it in a sudden, dramatic burst. A classical nova, for example, happens when a white dwarf in a binary system steals gas from its partner. This stolen hydrogen builds up on its surface until it ignites in a thermonuclear explosion. It's not the star's death, but a violent reminder of the explosive power it holds within. And of course, there are the even more spectacular supernovae. These explosions are so powerful they can outshine an entire galaxy, appearing like a brilliant lamp switched on in a dark room. Variable stars, in all their forms, are windows into the secrets of how stars live, breathe, and die. They make the universe a dynamic, ever-changing place, filled with light that beats to the rhythm of a cosmic heart. But there are objects in the universe that go beyond even these dramas. Enter the magnetars. These are cosmic monsters, neutron stars with a magnetic field so unimaginably powerful that it bends the very laws of physics. An ordinary neutron star is already an object of incredible density, but a magnetar is its more extreme cousin. It's born from the collapse of a massive star, but it emerges with a magnetic field 1,000,000,000 times stronger than a refrigerator magnet. This field is so intense it could wipe your credit card from hundreds of thousands of kilometers away. Near a magnetar, reality itself is warped. Atoms are stretched into thin spindles, and electrons are forced to move along magnetic field lines like trains in a tunnel. It's a reality completely alien to our own. A magnetar doesn't need visible light to announce its presence. It reveals itself in moments of pure fury, brief, violent bursts of gamma and X-ray radiation that scream across space. When its super hard crust cracks under immense magnetic stress, it unleashes an amount of energy in a single second that our sun would take 100,000 years to emit. These events are so powerful they could disrupt Earth's atmosphere if they happened close by. Between these outbursts, magnetars rotate slowly, their spin gradually slowing down over time. Their immense magnetic field acts like a brake, scattering energy into space and slowing their rotation. Each slowdown is a testament to the colossal forces at play. Magnetars are proof that the universe loves to push things to the absolute limit. They are a boundary, a test of the endurance of matter, and a place where reality bends under its own weight. Finally, let's travel back in time, to the dawn of the cosmos, to meet the very first stars. These were not like any stars we see today. They were true cosmic colossi. They formed in an era when the universe was filled with only hydrogen and helium. Without heavier elements to help gas clouds cool and fragment, matter collapsed into gigantic clumps, forming stars with hundreds, or even thousands, of times the mass of our sun. These supermassive first-generation stars lived life in the fast lane. Their cores were so hot that nuclear reactions blazed at an impossible pace. Instead of calmly burning for billions of years, they burned through their fuel in just a few million. They shone with an intensity that could illuminate the early universe across vast distances. Their immense power was also their doom, as their lives were dramatically short. But in their brief, brilliant lives, they performed a miracle. They were the first forges of heavier elements. In a universe made of just hydrogen and helium, these stars created the first atoms of carbon, oxygen, nitrogen, and silicon. The rich, diverse cosmos we see today exists because these primordial giants began the process of making reality more complex. They created the building blocks for future galaxies, planets, and, eventually, for us. From the quiet embers of brown dwarfs to the raging fury of magnetars, the universe is a place of endless variety and wonder. Each of these celestial objects tells a unique story, revealing just how creative and sometimes extreme nature can be. In the cosmic theater, where everything seems possible, some stars set records that defy human imagination. Some grow to such absurd sizes that if you placed one at the center of our solar system, its surface would swallow Earth's orbit, or maybe even stretch beyond it. The largest known supergiants, like Uwe Scuti, aren't hot, violent monsters. They're red, swollen giants, so vast that light needs hours just to cross from one side to the other. Their outer layers are so loose and diffuse they're more like a gaseous mist, drifting to the rhythm of a pulsing ancient heart. On the other side of the scale are the record holders for mass, and these are anything but lazy giants. The most massive stars we know can weigh over 200 times more than our sun. They roar with energy, their surfaces scorching hot at tens of thousands of degrees, and their brightness can outshine our sun millions of times over. They live in a furious hurry, a short-lived explosion of light that burns them out from within. But records aren't just for giants. At the other extreme, you find stars so small and inconspicuous they could almost go unnoticed. These are the red dwarfs, barely massive enough to sustain nuclear fusion. They're like tiny flames burning with the utmost economy just above the point of going out. Their diameters are smaller than Jupiter's, and their surfaces glow with only a tiny fraction of the sun's brightness. But here's their secret: they are the true masters of longevity. While the giants live for millions of years, these tiny stars can smolder for trillions, far longer than the current age of the universe. Between these extremes, the cosmos showcases a panorama of phenomena that forces us to redefine what normal even means. Stars larger than we can imagine, stars so massive they're on the verge of tearing themselves apart, and stars so small they're like dying embers in the dark. Each one pushes the limits of physics, showing us just how far matter can go before it says, "I can go no further." For most of human history, we looked at the stars with our naked eyes, weaving myths and stories to explain the night sky. It was a beautiful but limited view. Then came the telescope, and everything changed. It was like piercing a thin veil between our senses and cosmic reality. Humanity stopped being just a witness and became a researcher. Ground-based telescopes were the first step. Placed on high mountain peaks, far from city lights, they battle Earth's trembling atmosphere, which blurs and bends the light from distant stars. Modern observatories, with mirrors the size of stadiums and amazing adaptive optics, can smooth out these distortions to reveal details no one could have dreamed of in the past. It was from Earth that we first measured a star's temperature, figured out what it's made of, and saw the first hints of its life story written in its light. But the real revolution began when we sent telescopes into space. Above the atmosphere, there are no distortions. Space observatories can see light across the entire spectrum, and this is where the great mystery deepens. Stars don't just shine in the light our eyes can see. They glow in infrared, ultraviolet, X-rays, and even gamma rays. Each of these invisible forms of light carries secrets about a star's temperature, its motion, and events so energetic they're hard to even imagine. With infrared, we can peer through dusty cocoons to see stars being born, witnessing their earliest, most hidden stages. With ultraviolet and X-rays, we see the hot, active stars, the ones throwing off powerful flares and violent explosions. X-ray telescopes show us a world of extremes: neutron stars, magnetars, and binary systems where matter spirals onto a dense core at nearly the speed of light. Each wavelength reveals a different layer of truth. Visible light gives us color and brightness. Infrared shows us what's hidden. Ultraviolet captures youth and intensity. X-rays speak of violence and energy. And radio telescopes detect the cold clouds of gas where stars begin, and the rhythmic beats of pulsars, the spinning hearts of dead stars. We're no longer just looking at points of light. We're seeing a space filled with diverse objects, energies, and processes. The visible world is just a tiny fragment of a spectacular, multidimensional show that's been playing out above us for billions of years. So how do we know all this? Studying stars is the art of reading light, because that's all we get. We can't touch a star or take a sample. The only thing we have are photons that have traveled for thousands, sometimes millions of years to reach our detectors. Yet from these tiny messengers, we can decode an incredible amount of information. The most powerful method is spectral analysis. When starlight is split into a rainbow, we see more than just colors. We see a code written in dark and bright stripes called spectral lines. Every chemical element, hydrogen, helium, iron, leaves its own unique fingerprint. By reading this spectrum, an astronomer can tell what a star is made of, its temperature, its pressure, and even how it's aging. It's like a cosmic X-ray, revealing a star's past, present, and future. We also learn by watching a star's brightness change. Many stars aren't constant. They pulsate, flicker, and dim in precise rhythms. Some expand and contract like cosmic lungs, their brightness rising and falling in a steady beat. These pulsating stars help us measure vast cosmic distances. In other cases, a dip in brightness can reveal a planet passing in front of its star, casting a tiny shadow. Sometimes, brightness changes because two stars are orbiting each other, one eclipsing the other. We also measure a star's motion. The Doppler effect, the same principle that changes the pitch of a passing siren, tells us if a star is moving toward or away from us. This tiny wobble can reveal the gravitational tug of an unseen planet, a method that has helped us discover hundreds of exoplanets. From its light, we can also learn a star's rotation speed, the strength of its magnetic fields, and the power of its stellar wind. Nothing escapes our detectors. And this brings us to the first stars, the true pioneers of the cosmos. Born in a universe that contained only hydrogen and helium, they were unlike anything we see today. They were true monsters, hundreds of times more massive than our sun. These first-generation stars lived fast and died spectacularly. Their death was even more incredible than their life. Some exploded as pair-instability supernovae. Deep inside, their immense energy created pairs of electrons and positrons, causing the pressure supporting the star to vanish. It collapsed violently, only to tear itself apart in a fraction of a second, spewing everything it had ever created into space. Others collapsed directly, forming massive black holes that may have become the seeds for the supermassive monsters we now find at the centers of galaxies. In both cases, the outcome was profound. The light of the first stars vanished, but the matter they forged seeded the cosmos with new, heavier elements complexity that had never existed before. Their explosions enriched the universe, allowing gas clouds to cool more efficiently and fragment into smaller pieces, forming stars like the ones we see today. They were a one-time phenomenon, a form of stellar life possible only in a brief, specific moment of cosmic history. They are long gone, but their influence is felt to this day. It's because of them that the universe became capable of forming planets, life, and eventually, beings who can look up at the sky and wonder about the beginning of everything. Have you ever looked up at the night sky and felt a sense of wonder? For millennia, stars have been our silent companions, guiding sailors across vast oceans and helping farmers plant their crops. They were our first map, our first clock, and our first book of stories. Long before compasses or GPS, ancient navigators read the stars like a celestial roadmap. The North Star was a steady beacon, a cosmic compass for explorers like the Phoenicians. The Polynesians took it even further, memorizing the rising and setting patterns of stars to navigate thousands of kilometers of open ocean. It was a skill passed down through generations, a testament to human ingenuity. On land, stars set the rhythm of life. In ancient Egypt, the appearance of the star Sirius heralded the annual flooding of the Nile, a crucial event that meant life and renewal. For civilizations from Mesopotamia to the Maya, the predictable dance of the constellations was the foundation of their calendars, their economies, and even their religions. The sky wasn't just a collection of lights. It was a living chronicle, a library of myths and knowledge written in starlight. As humanity evolved, so did our questions. The stars inspired philosophers to ponder our place in the universe, sparking the birth of astronomy. This ancient science, born from simple observation, would eventually lead to revolutionary ideas that reshaped our entire understanding of reality, from the heliocentric model to the laws of gravity. Even today, in our age of advanced technology, stars remain our ultimate guides. Spacecraft hurtling through the void use devices called star trackers, which are essentially cosmic GPS systems. They identify star patterns to navigate, just as ancient sailors did. From the first human who looked up in awe to modern astronomers peering into the dawn of time, the stars have been our constant guide. But for centuries, we were like someone peering through a keyhole, only seeing glimpses of the cosmic spectacle. The real revolution began when we learned to see the invisible. Astronomers often say that studying the stars is like reading a language written in photons. And with each new instrument, we learn a new dialect, a new melody in this cosmic symphony. First came infrared telescopes. They allowed us to pierce through the thick, dark dust clouds that once looked like empty voids. And what we found was breathtaking. These nebulae weren't empty at all. They were bustling stellar nurseries, workshops where new suns are forged. We saw that the universe isn't static, it's a dynamic place of constant creation. Then, we opened our eyes to the high-energy universe with X-ray and gamma-ray telescopes. This revealed the most violent and extreme events in the cosmos. We witnessed stars dying in cataclysmic explosions, stellar flares hundreds of times more powerful than our suns, and matter spiraling into the crushing gravity of neutron stars. We even detected gamma-ray bursts, the death cries of massive stars, so powerful they outshine entire galaxies for a few brief, brilliant moments. Radio telescopes, once considered oddities, showed us a universe that's completely invisible to our eyes. We heard the rhythmic pulse of pulsars, rapidly spinning neutron stars acting like cosmic lighthouses. We mapped the hidden spiral arms of galaxies and even found faint echoes of the Big Bang itself, the afterglow of creation. But the most profound shift in our perspective came when we took our observatories into space. The Hubble Space Telescope gave us our first clear views of galaxies that formed when the universe was just a fraction of its current age. And now, the James Webb Space Telescope is pushing those boundaries even further, unveiling the very first stars and galaxies to emerge from the cosmic dark ages. We can now study the atmospheres of planets orbiting other stars, a feat that was pure science fiction just a generation ago. And it's not just about light anymore. We've developed a completely new sense to perceive the cosmos. Gravitational wave observatories like LIGO and Virgo don't see the universe. They feel it. They detect the subtle ripples in spacetime itself, caused by the collision of black holes and neutron stars billions of light years away. For the first time, we are not just watching the universe. We are listening to its rhythm, its vibrations, its deepest secrets. Each of these tools has peeled back another layer of the cosmos, revealing a universe more vibrant, more violent, and more magnificent than we ever imagined. What was once unknown has become visible. What was once theoretical has become observable. And what still lies hidden in the dark awaits the next generation of instruments, the next generation of explorers, ready to push the boundaries of our sight and understanding. From a simple guide in the night sky to a source of profound scientific discovery, the stars contain the entire history of human curiosity. They are a symbol of our dreams, our ambitions, and our unyielding quest for knowledge. And as we continue to read this oldest of books written in light and gravity, we learn not only about the universe, but about ourselves and our place within it.